This is Professor Corey, and this lecture is our second lecture for Chapter 16, Acid-Base Chemistry. In our previous lecture, we explored several definitions for acids and bases and emphasized the Bronsted-Lowry definition, where an acid is defined as a substance that donates a proton, while a base is a substance that accepts a proton in an acid-base reaction. We quickly moved to pH and the relationships that are covered in this slide. Notice this slide uses H+ instead of H3O+, and realize that these are equivalent. In other words, H+ is equal to H3O+, the hydronium ion. The reaction shown here is called a hydrolysis reaction, and it involves reacting a substance with water. We represented an acid as HA, and since it is an acid, it donates a proton to water, forming the hydronium ion and the conjugate base of the acid. We can write an equilibrium expression for this reaction as seen at the bottom. Water is left out of the expression because it's a liquid. A strong acid will completely dissociate into ions when reacted with water, resulting in a very large K value, and the reaction would be written with a single arrow. This reaction represents a weak acid. Since it only partially dissociates, we will have an equilibrium. We can also write a hydrolysis reaction for a base. See how the base, represented as B, accepts a proton from water, forming the conjugate acid and the hydroxide ion? The presence of this hydroxide ion is what makes the pH basic. Two reactions are shown, with the first being the hydrolysis reaction of the weak acid H2S. The conjugate base of this weak acid is formed, and the second reaction shows the hydrolysis reaction of this conjugate base in water. The second reaction may appear to be the reverse of the first, but it is not. It is simply the hydrolysis of the conjugate base HS-. So what we have here are two hydrolysis reactions for a conjugate acid-base pair. Adding these reactions together results in the reaction represented by the auto-ionization of water. This reaction has an equilibrium constant that we call Kw. The relationship will hold true for all conjugate pairs. The Ka for the acid times the Kb for the conjugate base will equal Kw, or 1 times 10 to the negative 14th. This is a table of conjugate pairs and their K values. Choose one that has neither a large K or a very small K, and then multiply it by the Kb of its conjugate base. And this will hopefully convince yourself that this will equal Kw every time. Notice the strong acids have the large Ka values, and this is logical because they fully dissociate into ions. We can rank acid or base strength based on the equilibrium constant values. This slide just summarizes the previous image. You'll want to have your table handy for homework and future exams. You'll be able to use this table. More summary here. You can pause the video if you want to read that. I'm going to move on. This problem has two questions. First, we're going to write the hydrolysis reaction, and then we're going to use the relationship between the equilibrium constants for conjugate acid-base pairs to solve for the Ka. I've got some thoughts here. So first, hydrolysis means reacts with water, but what we need to know is if pyridine is an acid or a base so that we can write this reaction correctly. Now notice that we were given a Kb value for pyridine, and that's a clue, and that's telling us that this is a base. So when we write our hydrolysis reaction, the pyridine is going to receive a proton from the water because it's a base. So here's our hydrolysis reaction, and because it's a weak base, we have an equilibrium. The presence of that hydroxide ion is what makes the solution basic. In order to find the Ka, we'll use the Ka times Kb equals Kw relationship, since these are conjugate pairs. The Ka is 6.7 times 10 to the negative 6. When we have a polyprotic acid, there's more than one donatable proton. H2S is an example. The hydrolysis reaction is shown with the Ka value. Since H2S is polyprotic, it can donate an additional proton, as seen in the second reaction. The K value for the second reaction is much smaller than the first, and this is the trend for polyprotic acids. The first Ka is always the larger. Equilibrium constants can be a little bit cumbersome and even confusing when we're trying to compare the size, when we get into negative exponents with the scientific notation. So a common method of comparing acid strength is to take the negative log of the equilibrium constant, like we did with the hydronium ion concentration to find pH. Well, here, if we take the negative log of the equilibrium constant, the Ka, we get a pKa. This scale is much easier for comparison, but we have to be careful because now the strongest acid has the lowest pKa value. Now, this lecture focused primarily on hydrolysis reaction and equilibrium constant values for acids and bases and the relationship with the conjugate pairs. In our next lecture, we'll demonstrate methods for determining K values for acid-base reactions. Stay tuned. Thanks for watching the Professor's DuBois channel.